Okay, today is 2.1, day 2, and we get to teach you the 12 basic functions. Now, the order that we do them in is kind of irrelevant. It's not like a number one function, okay? But I will tell you the easiest of them all, you already know, and that's f of x is like y. Would you agree that f of x and y are kind of the same thing? All right, so then what they really say is f of x equals, it's like they're saying y equals. What is the simplest of all of them all? Yes. Y equals x, yeah. That's a really, really, really simple one, right? Okay, what's some other ones? And they're not going to be in the same order unless you're amazingly, or you look ahead on those slides. But don't do that. Just what's another one that you know? Y equals x is a simple one. And by the way, just in case you've forgotten, y equals x generally looks like that, with a slope of 1. It's 0. Yes, sir? X squared is another biggie. Okay. I know everybody knows x squared, and that's a parabola. Generally looks like that. Yes, sir. X cubed is another biggie out of my 12. X cubed, and that's, I sometimes call it the John Travolta function because it sort of looks like his classic dance move in Saturday Night Fever. Yes. Square root of x. Yes. Square root of x looks like this. And then we're going to have nice pictures of all of these in a minute. But okay, so there's some of the biggies. Got any more? Yes, sir. 1 over x. In case you've forgotten, this one starts to get a little more obscure. 1 over x kind of looks like this. And it's the first time where we have two different like lines. It's not just one continuous drawing. This one's got two separate things. You know another one? Ah, yes, absolute value of x. I know you guys have seen this one in higher algebra. Generally looks like that. The V shape. Okay, kind of like a parabola, or kind of like a yeah, kind of like a parabola, except it's sharper V. Absolute value of x. Awesome. As I'm guessing that's going to be the end of what you guys already knew ahead of time. Okay, so you're going to learn 6 more like that, and you're going to be expected when I say, oh, what's the natural log graph? You'll have to be able to do. Okay, I know what that looks like. All right. Just like if I say what's the square root graph, you're expected to already know those. All right, so let's go through the 12, and there's going to be some repeats in here, and some things you probably didn't know about them. Like this is the y equals x function. It's also known as the identity function. And one of the big things I need to get into your head here is to talk about these in the context of domain and range, because the problems that you have for today for your homework are all about domain and range of these functions. Except we're going to say, like, what if you took this equation right here and shifted it somewhere, and then I'm going to ask you its domain and range. For right now, what's the domain and range of this as it is? Domain, range. This is what I'd like you to do on each slide, is I'd like you to write down the domain and the range of that graph. Would you agree that the domain goes forever to the left and forever to the right, thus negative infinity to infinity? You with me on that one? Okay, how about up, down? What's the lowest it goes? Negative infinity. What's the highest it goes? Positive infinity, so there we go. Very simple domain and range, everything. Okay, moving on. This guy, domain. Negative infinity to infinity. How about the range? 0 to infinity. What if I were to shift it plus a? Would you need to know if a was positive or negative? Yeah, because if I go plus a, but a is a negative, that actually means you're going down, right? Okay. If this was simple, and that's the best advice, is just pick a simple number for it. Like if I say a, just act like, okay, well, if you know a is bigger than 0, then let's pick a number like 3. Do you get the thing just shifts up 3? So then my new range, my domain would still stay the same because this thing moved up 3. It's got the same domain. It still goes forever this way and forever that way. Okay, but its range would be different, right? Now it would be from 3 to infinity. But do you remember we started by saying a? I really don't know how far we shifted it up. And so therefore I can't say it's from 3 to infinity, but I could say it's from a to infinity. Because I don't know how far we shifted it up. I just know that we shifted it up some distance here. It turns out that distance is a, Again, it could be 3, could be 7, could be 1.2, I don't know. But I know now that the range would be different than it was before because it's been shifted up. My range used to be from 0 to infinity with a bracket on the 0. This is the easiest way to do this, is just start with what the range was. And then you say to yourself, okay, how did it change? Well, it's up from there. And it's some number, but don't pick the number that you just randomly picked, like 3. You got to say, hey, to infinity. As long as it's moved up exactly 3, do you get that if it was touching here, it's still going to be touching there? So yes, it'd still be a bracket. All right. On this slide, it didn't say anything about shifting it. I'm just trying to get you in that mindset of, what if we were to take this function and shift it somewhere? But I didn't say exactly how far. I said shift it A to the right. Well, you have to be able to say, okay, well, and now my range would be this. Or now my domain would be that. Just to clarify, if I did shift this A to the right, and I don't know exactly how far that was, looks like about 4.1 or something. Does it change its domain? Does it change its range? Sometimes when you shift it, it doesn't change either one. Domain still from negative infinity to positive infinity. Still goes forever this way and forever that way. And the range still goes from 0 to infinity because I didn't move it up or down. So moving it to the right doesn't actually change the domain and range at all on the squaring function. Okay, move on to this one, the cubing function. This is x cubed. This has a special thing that almost no other of the parent functions have, and it's called an inflection point. That point is special because it's always rising, as in this graph is always increasing because we only read from left to right when we're deciding whether or not something's increasing or decreasing. This one's always increasing. But at that point, do you agree something special happened at that point? It stopped increasing at one rate and changed to the other rate. It was increasing at an ever decreasing rate. It started to slow down and slow down. It's still going up, it's slowing down. And then it starts speeding up after that. So that was a special point. It's like if I'm moving from here to that wall and I'm going faster and faster, and then I start to slow down, and then I start to speed up again. Those would be inflection points where I'm still moving towards the wall, but I'm changing my speed from faster and faster to slower and slower, and then, all right. So an inflection point is a worthy topic of conversation. Next one, the reciprocal function. This is 1 over x, the 1 over x function. So what if I were to say 1 over x, but then I also say plus 2? The whole thing moves where? Up 2. What if I wanted it to move right 2? I would put it in here. That would move it right 2. Okay? Now, what if I were to say right a? I'd have to clarify that a was bigger than 0, otherwise it's really not right. It would actually be left. If I go minus a, where a is a positive number, this thing has to move to the right, however far a is. Do I know how far a is? No. But if I take this function and I shift it to the right, some amount, I'm not exactly sure. Do you get, if I'm just shifting it to the right, that its range isn't changing? If I just shift it to the right, its range isn't changing. It still goes from negative infinity. Let's actually clarify that. What is the range on this thing? Domain, range. I'm going to give you just a second to try it without me. I'll warn you, the domain on this thing is not from negative infinity to positive infinity because there's something along the way that doesn't work. So you have to write it for me in 2 chunks. This union that. Okay, would you agree furthest it can go to the left is negative infinity? Okay. But then as you move to the right from there, you eventually come up upon a spot where you can't go. Like you keep going, but then all of a sudden there's this spot here where it's like no man's land. You can't go in there. So it can't be what? 0. So I have a parenthesis around that. So it goes from negative infinity up until 0, but it can't be 0. And then it starts working again right after 0. So you'd say from 0 to infinity. Raise your hand if you had that. Awesome. Okay. Now, the range. Same idea. It goes forever down. You know, as I follow this guy down, it's going to go down forever, negative infinity, until where will it stop working? As I'm moving up, 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 I just can't get to what's the spot I can't get to? 0 again. Union starts working again at 0 to infinity. So now, let's imagine that I took this thing and shifted it to the right. I don't know how far. Let's say that far. How far is that? Let's say it's A. Okay, I shifted it A to the right. Did my domain change? Yeah, because it used to be I couldn't be 0. Now I can't be like, I'm not sure exactly what that is. So what do I say? Hey. So this works from negative infinity until, I used to be able to say 0. Now it's some unknown number over here. So I say it has been, now goes, the new range goes from negative infinity until it hits A. And it can't be A, just like it couldn't be 0 before. And then it starts working again at A and goes to infinity. So pretty much, what happened? This number changed to an A because I shifted it to the right. By shifting it to the right, did I even affect my range? No, because the range still goes up until 0, and then it can't be 0, and then it goes from 0 to infinity. So the range doesn't change. Yes. Okay. All right. So that's called the reciprocal function, and we're doing in the midst of each of these, I'm talking about that whole shifting at A business, so that when we get there, it won't seem so confusing later. If I just go through the functions with you, it feels really, really easy until the very end, and then all of a sudden it gets hard. So I'm showing you the hard stuff in the middle. Okay, so this is the square root function. You've already seen it before, right? Would you please write its domain and range as it currently exists? Remember, domains are this way, ranges are this way. Okay, so you should have said from 0, and can it be 0? Yes, you can have the square root of 0. That's legal. 0 to what? Infinity. Good. And the range, how low does it go? 0 to how high? Infinity. Can it be 0? Yep. There we go. Now, let's say I shifted this thing up A. Could you tell me what my new domain and range would be? If I shifted it up A, assuming A was positive. Okay, so I don't know how far I shifted it up. So let's say it's sort of like that. There, I shifted it up A, which turns out maybe was like 1.5, whatever. I don't know exactly how far up it was. So then, is my domain affected at all? No. Is my range affected? Yes. And how low can it go now? A to infinity. All right. Let's make it just a little harder. Let's say I said, I didn't just shift it up. Let's say I did this to it. I did negative A times the square root of x, where A was a positive. I'm like, what? But you said negative A. Yep. If A is positive and I did that, what you really need to do is picture where the graph is. Try to figure out where that graph moves to, and then you'll know what its new domain and range are by looking at the graph. Ah! My alignment's off, sorry. Undo that. And I was trying to just delete that little thing. So, okay. Do you remember that a negative makes the whole thing flip up, down? So that would go like this. And then the A on the outside is a stretch. So then it makes it stretch. So maybe it's, instead of being copied just like the other one, maybe I'll stretch it down more. What's its domain and range now? Well, its domain is still from 0 to infinity. How about its range now? Now what's the lowest it goes? Negative infinity, up until what's the highest it goes? 0. Notice that A didn't be involved in my answer for my domain and range. Because how much I stretched it didn't matter. Okay. All right, let's move on to this guy. This is one of the newer ones for you, the exponential function. Remember how we knew 6 out of the 12? It's one of the guys you didn't know before. But from now on, you're expected to know. So take whatever kinds of notes you need to so that you can remember this thing. Have you ever heard of exponential growth? And do you get that this is exhibiting exponential growth? After 0, as in this origin right here, after x is 0, from there on, it's kind of your normal, most people only graph the growth part, right, up there. Okay, well, it was actually growing the whole time. It was slowly rising as it came from the left. And by the way, there's an asymptote line across there, meaning it can't be 0. It's infinitely close to 0, but it can't be 0. All right, so that guy's the exponential function, and it's based on e. E is a neato little number. It's about 2.718. Let's write that down by where the e is, 2.718. But that's kind of like saying pi is 3.14. Do you get what I mean by that? Pi goes on forever and never repeats. So does e. E isn't 2.718, but that's how it starts. And then it goes on and on and on and on and on. And it's a really cool number that's found in nature. It can be found in, when they're doing populations, they use a special thing called the basic logistic graph, which you'll learn in a minute. And it's got e in it also. Populations are usually have a limit to them. In other words, you couldn't have an infinite number of rabbits in your backyard. Eventually there'd be a limit to how many you could hold, and the rabbits would stop reproducing, or a bunch of them would die off, such that there would be a limit to the population. Okay, so anyway, the exponential, the e here, is going to come up again in another one of the functions. But this is exponential, as in it will go on forever. What's its domain? How far this way will it go? Forever. How far that way will it go? Forever. Negative infinity, positive infinity. How about the range in this guy? 0, but not counting 0. So 0 with parentheses. 2, infinity. All right. You really might want to write these down, because in a minute, you're going to get to your homework, and then if you didn't remember what the domain and range are, or if you, actually, I'll say it this way. If you have the domain and range already written down for them, when I change them and just say, oh, now move it up A, it'll be easy for you to do. Because this one went from 0 to infinity, and it can't be 0. Do you get, if I change it and I move the whole thing up A, does the domain change at all? No. Does the range change? Yeah. And it changes from 0 to infinity to A to infinity, however far up I moved it. All right, moving on. The natural log function. This one is a lot like that exponential function. In fact, if you dig into it deeper, the exponential function goes like this, and I missed its spot. It always touches at 1 right there. And this one always touches at 1 on the x-axis. And they are exact reflection of each other across the line y equals x, which means they are inverses. Don't worry, that's not something on the docket for today. I'm just telling you that there are functions that are called inverses, which are an exact reflection across that line. So this one and the last one are kind of tied together, exponential function and this one. Why? Well, the other one's got an e in it, right? Y equals e to the x, and that's the exponential function. This is the blue one here. This blue one has ln x, but in case you've forgotten this, we did it in honors higher algebra if you were in that class. ln means log base e of x. That's why they both have an e in them. Log base e is the same as ln, natural log. All right, in case you're wondering how to remember this one, well, you can memorize them any way you want to, but I personally kind of like this one. Would you agree that logs and trees are related to each other? Okay, and so if I take this and think of it as a tree, and trees have roots, right? They go down into the ground, okay? And then, but a tree isn't a log. But once a tree gets blown over by the wind, and it's like blown over in the wind, and it lays on the ground long enough, eventually you say, oh yeah, it's a big log over there. Okay, so anyway, that's a way to remember what the log graph looks like. And logs are very natural. Okay. Dumb way to remember it, but it might stick for some of you. All right, sine function. There's sine and there's cosine. If I go between sine and cosine, you'd find here, I'll flip between the two. Just look at the board for a second. There's that, and then there's that, and there's that, and there's that. Do you see how the difference between the two is just that one is shifted compared to the other one? It's just shifting left, right. Otherwise, its range and domain are the same. What's the domain on this puppy? Well, how far does it go this way? It's got an arrow on the end, just to clarify. Negative infinity to positive infinity. It's all real numbers. And the range? Well, it doesn't go way down. What's the lowest it goes? -1. Does it touch -1? It does. There's no asymptote line down there, so that's generally a sign that it will touch that spot. And the +1 is the high end. -1 to +1. Okay. So, what if I were to take my sine graph and go like this to it? +2 on the inside by the x. Is that going to be a left-right kind of thing or up-down kind of thing? Left-right. Okay, so is this left or is it right? It could be left. Now, would that affect its range, the up-downness of it? No, if it's shifted left or right here, I'll just draw it quick and then shift it. So there's it, and then if I shift it to the left or whatever, its range is still from -1 to 1, right? Ooh, that was loud. Please don't do that again. And the up-down, if I moved it up-down, that'd be like doing this. +4. That means the whole thing got moved up. Now, would that affect the domain? No. Would that affect the range? Yes. Just moving it left or right didn't affect the range a bit. It would still be from -1 to 1. Okay, so that first change, the +2, that did nothing. Didn't check the domain or the range. But when I did that +4, the whole thing would have to move up 4, be like that. Now its domain's still the same, but its range would be from, well, I'd have to do some complicated figuring because it used to be -1 to 1. Now it moved up some amount. I don't know. What's the highest that it could go? Well, it used to be highest was 1, and now it's 1, say it in terms of A, 1 plus A. And then the lowest it used to go was -1. That's moved up, so you'd say the lowest it goes is -1 plus A. All right, good. All right, moving on. The cosine function. How do you tell these apart? Well, the sine function started at 0, 0. Let me show you there. I'll go back here. See how it touches at 0, 0? The cosine function, when you're at 0, it starts at 1. That's how I tell them apart, because otherwise they are the identical curve. It's just been shifted. Okay, so try to remember that sine has nowhere to go but up. Okay, because when you start sine, you start usually graphing it right there, and it only goes up from there. Okay, cosine, it's all downhill from there. Cosine just starts immediately heading down into the valley. Okay, so if you can remember those two, I'll be asking you at the end. I'll be asking you, okay, so what's the difference between sine and cosine? Try to remember that sine, it's always looking up, and cosine, it's all downhill. Okay, absolute value function. You guys know this one. Interesting fact, this function has an abrupt change of direction or a corner at the origin, while all of the other ones were smooth. I believe that is called a cusp, but I am not positive of that. You will not be asked exactly what that's called. But it is not an inflection point. An inflection point implies that it's going the same direction. Like, see, this is going, it's decreasing, and then all of a sudden, instantly, it changes to increasing. That's not a point of inflection. Inflection is where you're going up, but you're changing how you're going up. Like that would be a point of inflection on this graph. All right. What's domain? Negative infinity, positive infinity. What's the range? 0 to infinity. What if I changed it to the whole thing got moved up A? Well, then it goes from A to infinity. All right. The greatest integer function, I've seen this one described as a GRINT, greatest integer, the GRINT function, okay? What does it do? Well, let's talk about its domain and range. Domain. Domain means it moves from left to right, and there's nothing it can't be. Is this domain truly from negative infinity to positive infinity? I want you to think. Think before you answer. Is there anything, any x that it can't be? So is it from negative infinity to positive infinity? Yes or no? Yes. Yes, it is. It is. Because at these spots where you're seeing an empty 0, it can be there. It just can be, it'll be up there. So it can be x equals 2. It just happens to be a little higher. All right. But the range is much more difficult to describe. The range, it can only be integers. Just in case you'd forgotten this number, it's another good ACT word. Integer just means can't be a decimal, can't be a fraction, has to be a whole number or negative whole number. That's why they don't call them whole numbers. Whole numbers are like 0, 1, 2, 3, 4. Integers are 0, 1, 2, 3, 4, and negative 1, negative 2, negative 3, negative 4, etc. Okay? So integers are like whole numbers, it's just they can be negative. So the greatest integer function, its its domain, is it can be negative 1, it can be 0, it can be 1, it can be 2, okay, but it can't be anything in between. So it's basically like a list of the integers. And no, I'm not going to be marking you wrong if you can't describe that perfectly in set notation, etc. But the domain can only be the integers. All right. The logistic function. This is that one I was telling you about with populations. Imagine for a moment that you had 2 rabbits, 1 male and 1 female, and they had a lot of time together and plenty of grass. All of a sudden, you got little rabbits running everywhere. And eventually, in the real world, rabbits are like the happy meal of the great outdoors. Everything likes to eat them. It's a nice little snack. Hawks like to eat them. Dogs like to eat them. I had a cat catch one once and would have liked to eat it, but we didn't let him. I mean, they just, rabbits, the reason they reproduce so fast is because everything eats them. Owls, hawks, lots of bird type animals love to eat them. So anyway, eventually, the natural predation is going to like make them stop, like their population doesn't go crazy. So it might start off, and in fact, I think this would be better if they made the graph more like this, because this is what happens if you give it a bigger top end. It starts off with exponential growth, and like right in here, the rabbits are just tons of them. They're growing like crazy, but then all of a sudden, things start factoring in, like they're getting munched, and now it levels off at some level. There was a guy named Malthus who thought that we were all not going to be able to, like we couldn't have this many people on the planet. He said it's just growing exponentially so fast that there's no way it can keep up, and he figured it would do this. Well, it hasn't yet. Would you agree that our Earth can maybe only hold so many, though? I mean, at some point, won't there have to be a limit to how many people? Okay. Now, right now, we've been able to do it by, I'll give you one stat that might help you understand it. In the United States, it used to be like 70 or 80% of the people in the United States were related to agriculture, as in just making the food for everybody to eat. Now it's down to 3%. Now think about that. If you take 70% of your people, we needed 70% of the people to be making that much food. You can see why Malthus was thinking we won't be able to keep doing this because there's not that much farmland, etc. But now we're down to only 3% of our people need to be making the food for everybody else. And they're getting so much more per acre than they used to. Just ridiculous yields on corn and the beans and whatever. Now, you can argue about whether or not those things are as healthy as they used to be. Some people are arguing that the food isn't as healthy as it used to be because, you know, and they probably have a point. We don't know. We won't know for probably a long time what the full effects of that are. But we're able to feed everybody. Malthus was wrong. Whether or not in the end you know, there's some limit to our population growth is a good question. All right, so anyway, this is like the limiter. Do you get how you can't cross an asymptote line? So in this function, if you decide that that limit is going to be, let's say, 100 million people can live in a certain country. We already have 300 million in ours, but okay, let's say it's a much smaller place, like Rhode Island. Most people we can get in there's 100 million, okay? Well then, the 100 million goes here. It's this top number is your limiting factor in this function. Notice it's got the e again. Try to memorize it. It is 1 over 1 plus, a lot of ones, e to the negative x. That's called the basic logistic function. And if you want to make this top number an L, that'd be okay because that's the limit to growth. So if they tell you that, oh, in our rabbit scenario, in the backyard, the most we can hold is 250 rabbits, then 250 would be your limiting factor, and it goes on top. And then you can model your growth of your rabbit population with y equals, or f of x is the same as y, right? Equals 250 being my limiting number. All right, moving on. There's so much I could tell you about these functions, but that was the 12 biggies. Let me just review the 6 that you probably didn't know before. Which one goes up starting at the origin? Sine, very good. And the other one must be cosine. What does it start at? 1. Starts at 1 and then makes a valley. Okay. So sine, cosine. Name another one that was new for you. Natural log. It's like a natural log tree that's been blown over. Can you sketch it in your head? That's the natural log function. Okay. There was one that was a lot like that that went the other way. Can anybody name this guy? The exponential function. Good. E to the x. And they are a flip of each other across the line y equals x, and that makes them, remember what it's called? Inverses. You aren't required to know that, but I'm just telling you for the future. This one's y equals e to the x. This one's ln x, which is also known as log base e. So they both have e's in them. What's the other one with e in it I just was talking about a second ago? It's called the basic logistic graph. What's the equation for that puppy? 1 over 1 plus e to the negative x. Very good. And that is the one that starts off with exponential growth, and then everybody starts eating your baby rabbits, and it levels off. Yes? Good question. What's the lowest it can go? 0. What's the highest it can go? That depends on you and how you set up the equation. You can call it L right here. So whatever number's right there is your highest it can go. Okay, so I could, if I label that as an L, I could say that my range would be between 0 and L. Okay. Now, let's actually get into some of these. This we did the other day, and it's all, like we already did this, but I want to review it with you real quick. If they tell you x, that's the simplest kind, like f of 4. So all I got to do is stick in a 4 right there. And that becomes 4 squared is 16 times 2 is 32 minus 1 is 31. Could you do that? Tell me you could do that. Okay, good. This next kind, f of x is 5. X equals what? Well, f of x, which is right here, is 5. So 5 equals 2x squared minus 1. Then I just have to solve it. And you just got to remember that at the end you'll get 2 answers for this because you're going to take the square root of a variable and you need a plus and a minus. So if I go plus 1, 6 equals 2x squared, divide by 2, 3 equals x squared, and then take it over from there. Yep. And then? Thank you for remembering the absolute value. And then? Yep, I'm just going to write it twice. Negative square root of 3. Okay, good. All right. Next part. F of x plus h. What? They didn't tell me an x. Actually, they did. They just told me a really abstract x. X is x plus h. So I'm going to drop in, instead of just an x, I'm going to drop in an x plus h. It'll be 2x plus h squared minus 1. And now the really common mistake is for people to go x squared and h squared. That's what this is, right? Just square both of them, right? No. Squaring something means times it by itself. So you'd end up with x plus h and another x plus h, and then when it's all done, you subtract 1. Okay, and then the other common mistake here is if you're putting in f of x, that's just this. But if you just write 2x squared minus 1, you'll forget to distribute the negative to both of them. So what should be really on this thing? Parentheses. That way this negative can distribute to both here and there, and it'll be negative 2x squared plus 1. Okay, so those are the common mistakes people make on that kind. And now here, this is that part where we take a function that we already knew, but we throw an a into it to make it really confusing. But it's really not that bad. You knew what y equals x looked like in the first place, right? So everybody sketch that. Just sketch a y equals x on there. And then you just got to think to yourself, all they're doing is taking the y equals x and they're moving it. Where? Down. How far? A. I don't know how far, but I move it down A. And if I wanted to label it on here, I'd say that from here to here is A. Now, I got to be careful as I write this out. My domain is still negative infinity to positive infinity. That's the whole point. Find the domain and range. The range. You might even want to write out what it used to be. The range used to be negative infinity to positive infinity. And then you say to yourself, by moving it down A, did that change my range at all? No, it really didn't. So I don't have to change my domain and range. Yay. All right, this next one is confusing enough that I am not going to mess with it. I don't believe we would do anything that challenging with you until quite a ways from now. So I found it just confused my last hour class too much. But this next slide is pretty good. Okay, take a look at this one. X minus 4 times x. The other one says x minus 4 times x2. What's the difference? Yes, ma'am? It's equal to different things. The one on the left is equal to what? 0. So really, they have set f of x, what's that also known as, by the way? Y, equal to 0. Do you remember what that does when you set y equal to 0? Gives you the x-intercepts. So this one will only give me the x-intercepts. There'll be 2 answers. Can you do them in your head? What are they? 4 and 0, because 4 makes this one part 0 and this one's 0. So 4 and 0 are the 2 answers. 4 and 0. That's the only 2 answers to that equation. But this equation has many more options. Do you get that this, when I multiply it out, would be x squared minus 4x? Okay. So if that's x squared minus 4x, that's like a parabola. Parabola, right? X squared. But wait a minute. We know that it touches, from looking at this, we know that it touches at 0 and 4. So I better move this guy over like that. Now that's the equation that goes through those same 2 points, but it has all these other things, so we have to draw a line that goes forever like this. Let me ask you, what's the domain on those guys? I should clarify. I'm talking about this graph right here. What's the domain on that graph? Negative infinity to positive infinity. And what's the range on that graph? Well, I'd need to know how low it went, wouldn't I? Okay. The range will go from however low that is, I don't know, until what? What's the highest it would go? Infinity. Okay, so then we got to figure out that. How are we going to figure out that low spot? That's also known as the local minimum. It's also known as the vertex. And I believe it's beyond the scope of what we need to learn for today, but the vertex form, we did something called complete the square. Does that ring a bell? We did something called completing the square that we used to find the vertex form, and once we found the vertex, we could tell what the lowest is that it goes. But again, I just wanted to talk about how you could see the 2 x-intercepts broken out because we set y equal to 0. as opposed to when you graph the whole thing, it goes forever. And no, I'm not going to take the time. It would take up all the rest of our time to remind you how to do the complete the square for the vertex form. Once we found the vertex, though, that would tell us how low it went. Okay, that's the end of our notes for today. Let's actually start homework problems. Okay, now remember, we had 2 days in one here, and we're on the second day of that. So we now have to fast forward through the other questions. There's our first question. This is the same one that I told you that we would skip, and we are going to skip it again. The rest of them, I want you to do. This first one is super simple. It's y equals x, except it's been moved down. How far? A. Where x is less than 0. Wait a minute. That's different than before. All right, so let's do this one carefully and fully. Okay, so there's, well, actually, it's not quite careful enough. I'm going to try again because it hits all of these spots. My alignment is off, which makes it really challenging to try to draw a straight line through those points. Now, if I move it down some amount A, where A is greater than 0, meaning that I'm moving it down a positive amount, like 3. The first step is to pick a small, reasonable number to deal with. Like, let's say I want to pick it to be like 2. I'm going to move this thing down 2. So I didn't mean to move that. I'm going to try to move this down a couple. There. Are you with me on that? I just moved it down a couple. How far exactly did I move it down? Okay, but in this problem, how far did they tell me to move it down? A. So I don't know how far it is down, but it's down A from where it was. This distance is actually A. So what would that point be? Would that point be A? Careful now, we went down, so it would be what? Negative A. That point right there would be negative A. All right. Now, next thing. It says that for purposes of this graph, my x needs to be less than 0. Here's where my x's are. Do you get if x is less than 0, then this whole right side, like from here on, can't exist? If x has to stay less than 0. And in fact, there's even still something wrong with my graph. What's wrong? Still touching at 0, exactly. So this spot right there needs to be an empty spot. Where is said empty spot? It's at x is 0 and y is negative A. Good. Okay. So now we got a good idea of what this graph looks like. Still goes down forever, right? Okay. So now, what's this domain and range? The domain's negative infinity until it hits what? Stops working at 0. Good. And then the range is from how low? Negative infinity till how high? Negative A. Very good. Okay. Here's another one. This one's been shifted. I want to call that right A. Do you get what I mean? Because it's minus A. And this is down A. And how far is that? I don't know. But I take my original, which generally looks like that. That's not very good. Generally looks like that. And yeah, it's got a stretch factor at 2. So how stretchy should I make it? Doesn't really matter. You'll find that stretch factors really don't matter much on these. And then I've moved the thing down A and right A. Down A, I don't know how far that is, but I'm going to call it A. And then right A. And now as long as you know that those two distances are A to the right and A down, now you can say what your domain and range are. I know the directions only say range. I want you to do the domain and the range for all of these. All right. And the good news is for you is that because this was in a very intense lesson, I am assigning all rest of the problems, but it's not even due tomorrow, it's due the next day. So you have 2 nights to get this done. Tomorrow in class, you'll be taking the top 20 again, and hopefully proving to me that you really have improved. If you haven't, you know you're still kind of stinking on those, we'll work on them tonight. Make that your homework. This can be done, you can do this tomorrow night, because there's nothing new coming at you. Okay? So tomorrow, after your top 20, I encourage you to just continue to work on this homework and ask for help from friends if you're not understanding certain problems. All right, that's all I have for you for today. That was a long lesson, though, 45 minutes long. Holy smokes.